Hi, hello, and welcome to material testing and fatigue characterization for Fatigue of Welds in nCode DesignLife. I'm Rob Plaskett, first I'd like to introduce why we're here today. Why do we need to do this material testing and fatigue characterization for welded structures? Why do we need this? Many structures have complex geometry with many joints between components with different materials or different thicknesses, and many of these are welded joints. These joints become stress raisers, so the durability of these joints are very important for the durability and reliability of the whole structure. This example shows the complexity of a car body with different components, spot welds and seam welds. Electric vehicles and also general vehicle lightweighting is driving the automotive industry in particular, and other industries as well, to reduce material thickness and or to use lighter materials like aluminium. Looking a bit more closely at why we need this, for automotive body, chassis and battery structures, there are many welded joints of different geometry and materials. For computer simulation and prediction of durability, we use nCode DesignLife fatigue analysis tools with material fatigue properties, providing a fatigue curve for use in the analysis. Fatigue simulation and prediction of welded joints is more complex and requires joint fatigue properties, not just material properties, that combine both the joint geometry and the joint material. This presentation describes some of the challenges for welded joint fatigue testing, particularly identification of failure location for the failure mode verification, and solutions using various camera systems and analysis methods to determine the stiffness changes due to cracks initiating and cracks growing in the test specimen. We will look at some different weld test specimen geometries, overlap seam weld, fillet seam weld, and coach peel spot weld, why these different geometries are needed, and how they are fatigue tested. Like many others, I've been working from home during this last year or so, and I've attended many online conferences and presentations, usually working through emails with headphones on, listening to presentations with a presentation on an external monitor. So to grab your interest, here's a quick video of a simulated spot weld fatigue test in coach peel to show where the cracks start and their direction of growth. This presentation will show how we develop these weld specimen geometries, develop the fatigue tests, and reduce what is gigabytes of images and videos into small presentable videos that can be used in a presentation like this as a summary, and how we use these to verify the failure mode and combine with the stiffness drop analysis for characterization and reporting. Okay, The agenda for today includes 1 and 2, which are a recap of previously recorded webinars. 1 for using nCode DesignLife for Fatigue of Welds, and 2 for introducing the AMCT, our Advanced Materials Characterization and Testing Laboratory, for fatigue, for a more detailed overview of fatigue testing and fatigue characterization. Agenda items 3, 4, and 5 describe the fatigue analysis for welds, the specimen design, the testing results and characterization. 6 looks at some of the camera and video challenges along the way, and 7 and 8 conclude with a summary and questions. But before we start, a little about Prensia. With Prensia, our software group within HBK, probably better known by our software brands, nCode for durability analysis, including fatigue analysis and associated signal processing and data analytics. ReliaSoft for reliability analysis, including life data analysis, reliability modeling, and failure modes effect analysis and criticality analysis. Our training and education includes design for reliability, design for durability, fatigue theory and hands-on software. Our services include materials testing, with the main subject of this presentation, and our consultancy services include design, development, and test for durability, asset management for reliability, and more. Looking at the Prensia software portfolio, we have ReliaSoft tools in the left column, containing tools for reliability analysis, with failure data analysis, test planning, and system modeling. In the middle column, tools for reliability management. So here we want to manage risks, maintenance, and actions. On the right-hand side, we have the nCode tools for durability, analysis of measured signals, vibration and acoustics analysis, and the last one being Akira, which offers a web portal for secure access to the measured data and the various analysis tools. For this presentation, we'll concentrate on nCode DesignLife with the material testing requirements to provide weld fatigue data for DesignLife weld analysis, and also show a little bit of nCode LiftWorks for image and video processing and reporting these test data. So I'll be first to recap a previous webinar, Introduction to nCode DesignLife for Fatigue of Welds. This webinar was originally presented a few months ago, 30th of March 2021, and a link to the recording is given here. This presentation highlights some of the slides from that webinar, but does not have the time to go through these in detail. I highly recommend watching this recording to see how these weld fatigue curves are applied within nCode DesignLife and the associated finite element modeling required to actually model the welds appropriately for the fatigue curves. Okay. nCode DesignLife is a computer-aided engineering tool for fatigue simulation prediction using finite element analysis results from solvers including ANSYS, Nastra, and Abacus, and others. It includes fatigue damage models for stress life, strain life, and fracture mechanics and crack growth with uniaxial and or multi-axial models. For quasi-static and vibration loading, for materials, from metals to polymers and composites, for isothermal and thermomechanical environments, for adhesive bonds, and for welded joints. Our main interest of this presentation today. First, some observations on general fatigue behavior of welds. Weld fatigue performance is usually different from the parent material for many reasons. The weld geometry and the weld quality can lead to stress raises and stress concentrations. The difference between the smooth CAD profile of a designed weld and the reality of a manufactured weld. Non-uniform material distribution, where we have deposited weld material, we have heat-affected zones from the heating and the cooling of the welding process, leading to modified grain structures. And most importantly, most significantly, high residual stresses as a result of the welding process. In addition, weld fatigue properties for fatigue simulation are difficult to obtain. They are harder to obtain than testing samples of the parent material. And weld fatigue durability is primarily a crack growth behavior because of the presence of pre-existing crack initiation sites. If the weld joints are not fully fused, and also the boundaries between the parent material and weld material. So this in a summary of this webinar, it described a number of different approaches for weld fatigue methods, for seam welds, a fracture mechanics based approach. This approach is often used in large or safety critical components. And where a damage tolerant approach is required. These kinds of crack growth methods are available in nCode DesignLife. Or a local approach, where these attempt to predict the stress or strain at a localized crack initiation site in the weld. This requires either a detailed model of the weld or using the stress and the strain from a less detailed model and applying those to a detailed model or using equations to actually calculate the local stresses. This requires assumptions and or idealization has to be made of the detailed weld geometry. The one we're most interested in here will be the structural stress approach, or the hotspot method. And this works from a stress which is in essence the maximum stress at the toe or the root of the weld, but excludes the effect of the stress concentration. Well, this is a KT factor, where this, together with other effects, is introduced by the weld, are effectively included within in the stress life curve, sort of actually for the weld itself. And it's this approach that we're going to concentrate on. Okay. So this previously recorded webinar describes how the structural stress method is used with a simplified finite element modeling approach to calculate forces and moments at the weld toe or the weld root. It describes both the finite element modeling requirements that are required to represent that particular weld configuration, and how the forces or the stresses are recovered sort of actually from those welds or actually from those nodes in the finite element analysis. I'm not going to describe the details of that here. This is all available in a pre-recorded webinar where you can see the link at the bottom of the screen in a moment. I'd highly recommend you watching it to sort of understand the process of how the weld curves are actually used within DesignLife. Okay. The second part of our introduction, again, with a pre-recorded webinar, is introducing the AMCT facility for advanced materials characterization and testing. So here we have a photograph of the AMCT lab at our offices in Sheffield in the United Kingdom. Here we can see a number of axial fatigue test rigs of in a range of sizes and capacities, a torsion fatigue test rig, and we have some with climate control chambers and also high temperature chambers for non-room temperature, non-ambient humidity conditions. So where do you get your materials data for fatigue modeling? Are you only doing a stress analysis? So do you only need the elastic modulus? Are you actually doing a fatigue analysis where you need the fatigue properties? Where do you get them from? Is it a literature search or a Google search? Are the properties within the company or organization or organization experience, where these are the fatigue properties that are used and have been used for a number of years? Do you get the material parameters actually from your material supplier. How and where you get your material fatigue data is very important and has an influence on the confidence that you can have within your fatigue modelling and fatigue predictions. Okay. Depending on where you get your materials data, it can be low cost or free. You might be looking those up as a literature search or in Google or in books. Is the information from a data book or standards? Has it come from a supplier in terms of a general supply or specific batch supply? Or do you test your specific material or test your specific material in its manufactured configuration? All of these have sort of increasing cost, but they also come with increasing quality assurance of having material fatigue data that's appropriate for your material and your manufacturing. For welded structures, we're looking at materials which include high residual stresses from manufacturing. So here we're looking at using fatigue test specimen components that are manufactured in the same processes as the resultant structure. Okay. Within the AMCT lab, there's a range of different material testing methods. I'm not going to read them all out, from static tests or fatigue tests, from specimens through to sub-elements and small components. And a key part of what is done by the AMCT is the materials characterization, which is the resulting characterization of the actual specimen fatigue tests or the individual fatigue tests. And that characterization derives the parameters for the various material models in nCode DesignLife for stress life or strain life or thermomechanical fatigue or whole life or welds. So it's that characterization which is really, really important for being able to take the fatigue test results to actually characterize them into a damage model that can be used within nCode DesignLife. If we look at a number of active research areas, number of lightweighting projects, which can be new joining techniques, self-piercing rivets, welds, adhesives, hybrid joints, different materials, polymers and composites, in different environments, and humidity and temperature, T-crack growth and additive manufacturing, and also considering model verification and validation. So particularly for welded joint structures, where the fatigue test specimen is essentially a sub-element or small component, and it's actually verifying that that particular specimen is correct for the that particular test purpose. In a sort of one-slide summary of fatigue testing, a DesignLife fatigue test rig, we see the grips holding a specimen. We see we see the gauge measuring the strain in the specimen itself. We have a load cell to actually measure the load. We have a test control system, so we can see so we can compare the load and the strain for each cycle. Okay. And we can see the waveform, in this case a sine wave. The results of multiple fatigue tests of individual specimens are individual points on the plot on the curve here in the top right, and that's just points to separation. There's then a lot of post-processing and further characterization to identify where the failure occurs as like a 10% load drop or 20% load drop. And that whole characterization is actually described a lot in much more detail in a previous webinar. So that's used to give reports for the each fatigue test. We do the characterization to we do the post-processing to identify the load drop, so we can sort of actually see the load dropping here. We determine whether that specific test is a plastic or elastic failure, and characterize the curves sort of actually from that. Okay, so that's introductions covered. I know there's quite a lot there, more detail than I can really go into, but those are two both our previously recorded webinars that you're able to watch. So if we look at a general fatigue analysis roadmap, we've got three inputs. We've got something about the loading environment, we've got the geometry or the shape, we've got material properties, and with that information we can do fatigue analysis, and we can get some fatigue results. As we work with welded joints, our geometry is combined with the material properties. So our material fatigue properties immediately start to include something about the particular geometry of that welded joint. So we test and break welded fatigue specimens in the lab to create a load life curve. Where we in an earlier slide, we showed a local approach where we use a detailed FEA, a detailed finite element analysis, to actually calculate a stress for an applied load. So this, so where we've got a detailed finite element analysis and we've got a local approach, then that's giving us a prediction of the stress. that we can use with a as the load life curve is converted to a stress life curve, so we can use that within the fatigue analysis. Now, we can't use exactly the same approach in the structural stress approach. So our fatigue analysis roadmap sort of actually changes a little for this. So here we have both our local geometry is combined with material properties, and our loading environment is combined with let's call it the macro geometry, and that's giving us a structural stress where that we can use. So this is where we have a simpler finite element analysis model, which is it is not modeling each weld in detail. In this example, we've got one shell element sort of actually for the weld itself. Okay. So what we need to do to develop material or equivalent material fatigue properties for a welded joint is we need to consider our real world structure, so our complex geometry, different thicknesses, our range of different materials manufacturing, and we need to define and design a fatigue test and design a fatigue test specimen that's designed to match that real world joint in both its simplistic geometry and its thickness. So it can be manufactured from the same material, manufactured by the same methods. And we need to do the same for the loading environment as well, where we effectively simplify the loading environment so that we can have a test for that's designed for that specimen shape and geometry. Okay. So our macro geometry is our weld configurations and our weld meshing requirements actually from our finite element analysis. So these weld configurations and weld meshing define particular failure locations, and so are they at the weld root or at the weld toe? So each configuration in the finite element modeling is specific to its potential failure locations. So whether that's is a fillet weld or an overlap weld. Okay. So for equivalent fatigue performance between where our designed weld specimen, we need to have an equivalent structural stress and equivalent fatigue properties to get equivalent fatigue performance. So the way that this is done is by developing two stress life fatigue curves, one for bending and one for membrane or axial stress. So by having two curves like this, where we have one for bending and one for membrane, we can interpolate between them for any ratio, or for any given ratio of bending stress to membrane stress. Okay. So our complex, in the real world, our complex loading and our complex geometry has a wide range of bending ratios. So we can so depending on the specific location and specific ratio for a fatigue cycle, we can calculate the unique stress life curve for that specific fatigue cycle, for that specific ratio of the bending and membrane stress. Okay, so it's that ratio that's important. So in pure bending, the ratio is 1. In pure membrane, and the ratio is 0. Okay. So all of the weld methods, or all the spot weld and seam weld methods within nCode DesignLife have a specific stress on the SN curve vertical axis. We have to take care to ensure that the calculated stress matches the SN curve stress, which come from testing. So when the weld test specimen is being designed, it's designed and it's built on the same kind of modeling techniques to recover the stress in the same way as the real world model. And when we look at resulting curves within nCode DesignLife Material Manager, we will see these some example curves in the material database for example seam welds and laser welds in sheet steel. Okay. So let's look a little bit at sort of actually developing a weld fatigue test program. We have to design the test specimen is designed and modeled for the application. So what's the actual joint geometry? What's the sheet thickness? What's the material? How's it manufactured? So a number of different weld types for overlaps, coach peel, fillets. We're usually designing 2 test specimens, one to identify or to get a good response, the membrane stress, and one for bending stress. And it becomes critical that we check that the failure modes agree between what is modeled in finite element analysis and what occurs within the physical testing. We need to define the failure criteria. Is the failure a visible crack in the weld, or or a percentage of the stiffness drop? Okay. So, as this example for a fillet seam weld, we might have 2 fairly similar but slightly different fatigue test specimens. So here the material thicknesses can be a little bit different, and they're designed to get the right failure or the right failure or the expected failure at a particular location at the weld toe. So we're looking for where that crack starts and what direction it grows in. We don't expect the specimens that are designed to have bending ratios or at the failure location to be pure membrane or pure bending. For this particular example, for our two specimens, the first has a bending ratio of about 0.8, and the second about 0.4. And these, their bending ratios need to be far enough apart so that they can be, so that they are distinct and can be separated actually during characterization. So, in a summary of the basics of the steps that we have to go through, we have to design a specimen, which is including finite element modeling and analysis of the specimen to make sure that the particular failure modes are in the right location, and there's a distinction between their bending ratios. Usually for welded joints, bespoke fixtures are required for the test rigs. And then it's only then that we begin to think of what's the test matrix, what's the type of test, what's the number of specimens, particularly in the first few tests that are run and developed with a new test specimen geometry, we're having to actually verify the crack start location and the crack growth direction. So we use cameras to sort of identify these and a number of different camera setups to identify and verify that. Then what the failure criteria is as a visible crack or a percentage stiffness drop. We've talked a little bit about test types and cameras, just to give you a little bit of a view on some of these. The first one here is for a tension test of a seam weld. The actuals, the specimens themselves are cross-hatched out. That first camera system is a Nikon. It's electronically switched based on numbers of cycles. The 3-point bending for the seam weld is using a pair of Raspberry Pis that actually move with the 3-point bend specimen. And a coach peel example for spot welds is using some video cameras. And the reason this is done is so that we can see exactly where the first failure occurs and the particular growth, and also the growth direction. Because when we've done our finite element modeling, we know where the expected first failure will occur and its expected direction. And we need to verify that the test specimen is designed correctly and the finite element simulation is matching the test specimen so that the two are so that they are fatigue equivalent. Okay. Just a little bit now on some of the results of these. So this is obviously a fatigue test can run for a long time. So this is just a simulated fatigue test for a seam weld with the center crack, where all images are appended one after the other to actually make a video. If we look at another way of viewing the same thing, we can make a much shorter and smaller size video, sort of actually by filtering the images, and we'll see a little bit more of that. So that gives us a smaller file for use as a summary to share. Depending on the specimen, we need to know if the crack's growing from the center or from the edge. And again, as we look at these in coach peel, we need to know where the crack is actually growing first. In this case, it's growing from the top surface. It could be growing from the bottom surface. What direction does it grow? Okay. I can't show you the real specimens, so I can show you simulated images and videos. Okay. So now let's look at a little bit of the test results and characterization for that. Obviously, we've got all the measurement information, the load, the displacement, the cumulative cycles, and the cycles to separation. But it's within the post-processing where we can calculate the stiffness. So here I'm using a normalized stiffness to identify the number of cycles to a percentage of stiffness drop. So are we looking for 10% drop or 20% drop? It's depending on the weld type, weld geometry, how this how quickly the stiffness drop curve develops is will change quite considerably depending on the actual weld, its materials, and its geometry. Okay. There's then some image post-processing to do to combine images to videos, being able to get them to a reasonable size that they can be emailed or emailed to the client or shown in PowerPoints or in presentations. And we have to review the videos to actually verify the test and verify the crack location. And that's particularly important for the first few tests. And then reporting that information. So obvious things such as the customer, the date, the job reference, material references, ID number, including the stiffness drop, and then including test images to add to that report that shows where and how those cracks were developing from the uncrack condition at the start of the test to a first visible crack by eye, a particular stiffness drop, and at the end of the test, just before separation. So all of that information provides for one single test for either a membrane, a predominantly membrane specimen or a predominantly bending specimen, gives us one set of test information which can be compared with our finite element analysis. And the characterization is developing those into their load life curves using the equations for the structural stresses, and then optimizing those to calculate the actual stress life curve that's going to be used for a given fatigue cycle. Okay, we are very close to the end now, so I'll just quickly do a couple of slides on the camera and video challenges. This particular example here, I was actually using a 3D printed bracket which is attached and moves with the rig with a pair of Raspberry Pis, such that we keep the same focal length between the camera lens and the weld itself. Here we've got a couple, a camera system with a wide field of view. We've actually got two cameras, front and back, or in some cases front and back or above and below, because we don't know which weld will actually get the first failure. So we have to identify that. Anything with either cameras and videos acquires large quantities of image data very, very quickly, and fatigue tests have long duration. So there can be thousands of high-resolution images which have a very large file size. The advantage of the videos is they're much easier and quicker to review, that, particularly to correlate the failure modes, to identify this, where the cracks start and where they grow, and being able to add on to those images the audit information, such as the ID number for the specimen, what's the test frequency, so how many cycles of fatigue test per second, in this case 2 Hertz, and also the cumulative cycles, so what's the total number of cycles that have been applied to that point, obviously a date and a time, and a frame number. Okay. I did say right at the start that a bit of GlyphWorks was used for the post-processing. So this is just some examples of GlyphWorks where, if we think of here, we've got 1,000 red crosses for every image or every frame in the video. Because from a fatigue perspective, we're more interested in having more images close to the failure, we can use a non-linear sampling technique to identify the particular frames that we want to use to actually make into a video. To make the reports, again, that becomes a GlyphWorks process where we can put through the image and the video information and the stiffness information, and produce the reports for those. Okay. Okay, as a quick summary and then some questions. The primary thing we have to do is identify that equivalent fatigue performance. So getting a loading environment combined with a macro geometry for the structural stress and a local geometry combined with material properties for the weld fatigue properties, and being able to separate those out as a bending as a bending SN curve and a membrane SN curve. Okay. Some examples of different weld fatigue test specimen models, and how these have to be designed to fit the particular weld that's being modelled, and then the final characterization and of the test results for the welded joints with the finite element analysis.